Hello. I'm going to talk about the signature of accelerated atoms in cavities. And this has been work with my supervisor, Eduardo Martinez and Don Page. And so in our group, we do relativistic quantum information, RQI. In that sense, so we are interested what is the context of quantum information in the context of relativistic quantum field theories. And in this sense, we will look at have a bit of a contrast to the usual way people look in quantum optics at certain models. And in a bit, I will explain more what this contrast actually means. So first of all, the motivation is, we heard already a couple of days ago about the Unruh effect and how can we detect it. To that end, a certain type of model and experiments are proposed in recent years. And I will introduce the model we will use to study that, is the Unruh-DeWitt model. And then I will talk explicitly about the single mode approximation and the dimensional reduction. And will tell you that these approximations are in general a bit dangerous to apply. So I need to stress again, even though we heard 2 days ago about the Unruh effect, because of its importance. So in the 70s, by people like Unruh, Davis, and Fulling, they described how in the vacuum state, so the lowest energy state of a quantum field, in Minkowski spacetime, an inertial observer will see no particles. However, an accelerated observer, on the other hand, will see a thermal bath of particles, which have a temperature T proportional to the acceleration. So there's already like a deep ontological concept in there, if you want, about the reality of particles. And I don't want to focus on that, but it's definitely something of interest. The main point is that the temperature of the thermal bath is proportional to the acceleration of the observer. And you can derive this effect in axiomatic QFT. You can use Bogoliubov transformations. You can use detector models. And so we have pretty much theoretical confidence that this is actually something that should be there. But the problem is experimental detection. So if you want to detect a thermal bath of 1 Kelvin, you need acceleration of 10 to the 20 meter per second squared, and that seems a bit difficult to realize. And so it's not very surprising that so far there is no experimental evidence. So in recent years, and also a bit earlier, people were proposing a certain class of experiments, and this is one of the recent ones by Marl and Scully. So this is actually related to the Hawking effect. So we have a stream of atoms falling into black hole. We have an optical cavity here, and the outgoing radiation observed by an observer at infinity should resemble the Hawking radiation. And most of these proposals have in common that they use some cavity QED, some cavity quantum electrodynamic system. And if you look at the literature, and not just especially for the Unruh effect, but also in the wider range of the literature regarding quantum optics, then there are often approximations used. So this is just one of many examples. Often approximations used that need further justification, and so we were led to actually investigate if the models people were using to propose an experiment were sound. And so one of them is the single or few mode approximation. So we know, if we have an atom that is energetically resonant with one field mode, then it seems reasonable that we throw out every field mode that is not in close resonance. So we don't have to deal with an uncountable set of other field modes. And the second one is, what is if in this context we have a cavity where one of the dimensions, spatial dimensions, it is much smaller than the other ones. So it seems very intuitive that we can treat it by a lower dimensional setup. And especially, how does it behave in the relativistic regime, where phenomena like the Unruh effect are important. And our results, and what I want to convince you of, is that in general you should not use this approximation in this setup. And that is a problem for many papers in the literature. So our setup that we use, we use a 3-dimensional cavity, and we model our atom as a two-level atom, so that could be a qubit, and is separated by energy gap omega. And this interacts with a massless scalar field phi, and okay, you see now this doesn't look like the usual electromagnetic interaction. So it's in fact the Unruh-DeWitt interaction. And this is a scalar simplification of the usual light-matter interaction. It is used extensively in many different setups fundamentally. So how do you extract information from a quantum field? So a detector model is an easy way to do that. So you extract local information in space and time with a detector model. And the detector model is also a way to have an operational approach to the problem of what is a particle in quantum field theory. Because a particle is, in this approach, just the thing, basically what is detected by a detector. So if the detector clicks, you have a particle. And it also allows for operational formulation of the Hawking-Unruh effect. And it is so as long as you neglect exchange of orbital angular momentum between the field and the atom, this is a pretty good simplification you can do. And then you have the interaction Hamiltonian. This is proportional to the coupling strength. Instead of the dipole moment, you have the monopole moment. And sigma plus and sigma minus are the SU2 ladder operators, which bring you from the ground to the excited state of the atom. So this was this energetic separation of ground and excited state. This is the tau is the proper time of the atom, and then we have the scalar field evaluated at the position of the atom. And now, or as we will see already in the weak coupling limit, our results hold. So you could think that, okay, if atom and field couple only weakly, we will not have so much problem with, for example, a single mode approximation, but it turns out to be the case. So we look at first at the energy spectrum in the field and transition probability of the detector after cavity crossing. We will look at the single mode approximation also in the case if the detector is just with constant velocity transversing, and we will look at the one-dimensional approximation. So first of all, the field solution. You have, just for completeness, because we particularize to a one-dimensional trajectory, so you only have two of the three quantum numbers contributing. L encodes the transversal degrees of freedom, and N the longitudinal ones. And then we can calculate the number expectation values in the field after the detector crossed the cavity. And now I will show you some pictures. So first of all, the plot here shows you what are the excitations in the field depending on the transversal and the longitudinal quantum numbers. And this is for non-relativistic trajectories. And here would say, okay, it looks like a resonance, as you would expect from energetic requirements. And so the single mode approximation should be good. However, if you go to high accelerations, you have the relativistic Doppler shift, and this looks much worse. And of course, if you have to go then to, if you want to study, for example, the Unruh effect, to ultra-relativistic regimes, and then looks totally lost. So this was when the detector starts in the excited state. However, it starts in the ground state, and even in the non-relativistic limit, nothing looks like a resonance, and so you would not ever expect the single mode or few mode approximation to be of relevance. And similarly, if you go to higher accelerations. Now I want to show you just this one plot about the constant velocity, because it's quite interesting. Not only do you see here that because the distribution in the field is relatively unhomogeneous, so it tells you first that you can distinguish it from the acceleration signature, which is interesting if you want to look at effects which are caused by acceleration, like the Unruh effect. And also, certain points in here are actually white, so that means the atom does not couple to the field mode, and this is called related to a phenomenon called mode invisibility. And this, in principle, allows you to do non-demolition measurements if you want to measure actually the field. And these are just telling you the same as for the other case, just that you have this oscillating behavior of the field modes. Okay. So this was more in a picture way saying, and now I want to give some more way to quantify it. So we take the transition probability of what is the excitation probability, for example, of the detector after crossing the cavity, or what is the probability that the detector spontaneously emits a quanta after crossing the cavity to leading order. And so then by using single mode approximation, what is resonant contribution to the total transition probability, and then you would expect it should be 1 if the single mode approximation is a faithful approximation. And exactly as we saw in the graphs, you see if this detector starts out in the ground state, never you should apply this. Even in principle it fails. And then, okay, non-relativistic regime for spontaneous emission, it could work depending on the parameter set, but if you go to more relativistic regimes, this will fail to hold. So dimensional reduction is something that we intuitively understand and do often in physics, because going to higher dimension in space and time is sometimes really tricky. You have to do a lot of integrals, and so you want to do it in a more simple approach. And so you could think, if you have our cavity, which is like a long fiber, long length and small radius, that we can't model by a one-dimensional cavity. And this is also done in other setups, I guess, in condensed matter and so forth. And we look at the frequencies of the field modes for fixed transversal mode number L, and we take the limit, and we get an effective mass. So first of all, not only do we have, so we start out with a massless scalar field in 3+1 dimensions. If we take the limit, then we would expect to have a massive field in 1+1 dimensions. So this is already introducing a mass. So we cannot model something higher dimensional by a massless scalar field. And then the reasoning could be, okay, the energy spacing becomes very large if we take the limit, and so becomes very large for modes of different quantum number L, and hence for different masses of the scalar field in 1+1 dimension. And so we would hope that only one effective mass or one quantum number actually collects all the distribution of the field to have a proper approximation. And as a measure of validity, we take the vacuum excitation probability and split it up into layers, basically of constant mode number L, and sum it up. And then we take the relative difference to see what is actually the contribution of the 1+1D model to the actual physical model. And we would hope to have something like f equal to 0. But if we go to lower and lower fraction of radius to length, so it would be micrometer to meter extension of the cavity, which is quite reasonable in an experiment. And we see it's not 0. And there are some numerical problems because it's a double infinite sum, and so we just can conjecture at this point that the limit will not actually be 0, because the peak of the distribution gets pushed to infinity. So, but we can definitely say that for this regime, it does not hold. Okay. So we saw that if we want to study as something as fundamental that we as the Unruh effect or Hawking effect, which really is something that we do not have in the usual regime that we encounter in daily life. So in this context, highly relativistic setups, we need to be very careful on what approximation we use, especially if we derive the intuition coming from different fields, which like quantum optics, which usually happen to violate the Lorentz invariance of the model. And so we saw that the single mode approximation is not a good approximation. We saw that the 1+1D model is in a wide range of regimes not a good approximation. And we saw that in principle we can distinguish the signature coming from the acceleration and the velocity. This may help for finding the Unruh effect in a cavity experiment. Thank you.
Thank you very much for that interesting talk. And questions, and who's got the box? No questions?